lot to Chiara and Marcello for organizing this very nice meeting and for inviting me again. I have very good memories of a similar event 2 years ago, where I also talked about the polaron, but about different aspects. So let me get right to it. I start with a picture that many of you have seen before, which is for those of you who like to have a physical picture in mind behind the model I'm discussing. This may be helpful. So this is called the polaron model, which is basically a model of an electron moving through a material, which you can think of as a crystal, and due to the electric charge of the electron, it polarizes the material. So you can imagine that at every point of the material there's sort of a polarization field, which in particular creates an electric field which then acts back on the electron. So it's a combined system of somehow an electron and a field, which is really the polarization field of this material. And microscopically you can somehow think that the material is composed of different kinds of atoms. Maybe these may be neutral atoms, but in the presence of the electric charge, the atoms can get polarized, right? They become little dipoles. Little dipoles themselves create an electric field which acts back on the electron. In the model you will not see a crystal because the model is what is called the model of a large polaron. So you should imagine that you sort of zoom out. The wavelength, the typical wavelength of the electron is much longer than the crystal spacing. So effectively we treat the polarization field as a continuum, and there's no more crystals. Okay, so that's sort of the picture to keep in mind. And the model describing this is known as the Fröhlich model. This goes back to the very early days of quantum mechanics, really. I think it was first written down in the 1930s. So let me just quickly walk you through this. So there are two components, as I said, right? So there's an electron and there's a field. So the Hilbert space is the usual L2 for the electron, and it's a Fock space over L2 for the phonon. So this is going to be a quantum field. This is going to be a simple version of the quantum field theory, because the polarization field will be described as a quantum field. And the model is defined by the Hamiltonian, right, the proper linear operator on this space, which consists of three components. One is simply the kinetic energy of the electron, which in suitable units is just minus the Laplacian. We're on R3, right, so this is free space. This is just multiplication by p squared in momentum space, so this obviously acts here. The electron. Now the field energy is this guy over here. I used the convenient sort of second quantization notation, so creation annihilation operators. This is on Fock space simply the number operator, actually, written out, so to say, in Fourier mode. So AK dagger, these are the usual creation annihilation operators. K is the index for the momentum of the field or of the phonons, if you want, right? So these A's and A daggers, they satisfy the usual canonical commutation relations. Okay? So this is just another way of writing the number operator on Fock space. You can think of this as basically like in the picture here. At every point in space, there's a harmonic oscillator whose excitation describes the polarization. Okay? So here, I mean, it's okay, this picture in every point in momentum space, there's a harmonic oscillator. So that's the free part. And then there's an interaction between the two systems, which is sort of in this linear coupling fashion. So there's phonons can be created or destroyed. So there's this linear coupling in the natural translation invariant way with an e to the ikx. And there is we call the form factor here, this 1 over k. That's typical for this model because 1 over k you should think of as the Fourier transform of 1 over x squared. And 1 over x squared is the interaction of a monopole, namely the electron, with a dipole. Right, so this is therefore the natural coupling of the system. The Hamiltonian has only one parameter, which is usually denoted by square root of alpha. Of course, you can put in other constants, but at the end they just scale out. So there's just one dimensionless parameter really that the model depends on. This is called the coupling strength. Right? And in particular, we will actually be interested in what happens for large coupling. So this is one of the, sort of the, I guess, very few quantum field theory models where you can actually say something beyond the perturbative regime, so in particular in the strong coupling regime. And I already mentioned, so this is called the Fröhlich model of a large polaron because the polarization field is already And here's just a minor technical remark. I mean, this is sort of a formal expression, right? If you think of this as an operator, its domain is not obvious because of this function 1 over k. Right here you effectively create a phonon with wave function 1 over k. This is not in L2, right? So this, the domain of this operator is actually non-trivial. It does not have any non-trivial intersection with the domain without coupling, which is sort of the trivial one. So, but you can, usually the way to do it is you convince yourself that on the quadratic form domain of the free model, this is well defined and bounded from below, and therefore by the usual abstract nonsense it defines a unique self-adjoint operator, and that's the one I mean, right? So this is just a formal expression. Okay, so this defines the model. Now what questions do we want to address? Basically, we want to do a spectral analysis of this operator. We want to learn about its spectrum, and more precisely actually the joint energy momentum spectrum, because this model is actually translation invariant. Right? It doesn't have any designated points. So it's translation invariant, which mathematically is reflected by the fact that it commutes with translations which are generated by the total momentum, right? So there's a conserved quantity, which is the total momentum of the system, which is simply the sum of the electron momentum, right, which is just minus I gradient, and the field momentum, which is simply, right, k is the momentum of the phonons, and A dagger A just counts how many phonons there are at momentum k, and you sum over all k's. So this is the total momentum of the field, and you can convince yourself easily that this operator commutes with the Hamiltonian. Right? So therefore, they can be diagonalized simultaneously, which in this case, where sort of there's purely continuous spectrum for this momentum operator, means that there's a fiber integral decomposition you can think of as the Hamiltonian as being decomposed into Hamiltonians for fixed total momentum, and these Hamiltonians for fixed total momentum are just written out here. And it's basically what you do is you simply, instead of the electron momentum, you write, well, the total momentum minus the field momentum, which is what it is, right? And then there's no more x in the picture, so by a unitary you can remove the e to the ikx, that wasn't the coupling factor here. And this way you just get a Hamiltonian that acts only on the Fock space. Right, so strictly speaking, there's a unitary which turns these fiber Hamiltonians into Hamiltonians just on the Fock space, and they are given by this 3-parameter family here, HP of Hamiltonians. Right? And the energy momentum spectrum is simply, well, you look for every momentum P, you can look at the spectrum of this operator HP. Right? And in particular, you can look at the curve, the lowest possible energy at given momentum, which is simply the E as a function of P is the infimum of the spectrum of HP. And so now if we just look at what happens in the trivial case without any coupling, right, where alpha is 0, then you can see there's sort of two cases. If you just look at the electron, meaning there are no phonons present, A dagger A is just 0, that's the vacuum, then of course the energy is just P squared. Right? That's the only thing that's left. But this is not necessarily the lowest energy you can do, because you could create one phonon. So this will cost you energy 1 here. And then with this phonon, you can give it momentum P, or as close as you want, so you can compensate this term. So you see also that there is spectrum simply starting at 1. So you can convince yourself that in the absence of an interaction, right, the lowest energy for given momentum, P is actually just the smaller value of P squared and 1. Right? So that's the picture to keep in mind. And this is what I was drawing here just now, because I will refer to this picture later on. Right? If you think of the energy momentum spectrum, that's sort of what it looks like, at least without any interaction. The lowest curve is the minimum of P squared. This is the parabola here, and 1. Right, so maybe I can indicate already here. This distance here is precisely 1, because that's in our units the energy cost for creating one phonon. And so the lowest energy curve here is simply this. And above an energy gap 1 above the ground state energy, right? So here is E0, well, okay, that was the notation, E0 of P, which is of course, sorry, E0 of 0, which is of course 0 now in this model, right? So here's 0, and up here is essential spectrum. So if you look at the joint energy momentum spectrum, there's an isolated curve here, the parabola which exists up to momenta 1, and then you have purely essential spectrum up here. This sort of corresponds to physically there being simply free phonons in the system. Right? And basically what I want to investigate is what happens to this picture now if we turn on the interaction, and in particular what happens for large interaction. Okay, and what I can anticipate is already is that basically what we will prove is that this picture qualitatively will persist. Quantitatively it will change quite a bit, because what turns out is that the whole picture moves down a lot. Okay, namely that the E alpha, so if you turn on interaction, E alpha of 0, which will still be the lowest point in this curve, this will be order alpha squared with a minus, so this will be very negative. This thing, however, will still be 1, so there will still be a gap of exactly 1 between the ground state energy and the essential spectrum. Okay, so this is easy to see, because this is just the energy cost of one phonon. That has sort of nothing to do with the interaction. The whole picture shifts down a lot by order alpha squared. And it turns out that even though the picture qualitatively persists, this scale changes a lot. So when you turn on the interaction, this length here, namely how far the curve has to go before it dives into the essential spectrum, will actually be also order alpha squared, as we will see. So that means this parabola, it stays essentially a parabola, but it becomes very flat. And this has to do with an increased effective mass of the system. So what happens is like the picture that if the electron moves through this crystal, it sort of surrounds itself by a cloud of phonons and becomes much heavier due to the interaction with the polarization field. And the stronger the interaction, the heavier it becomes. And in fact, what we will prove is that the effective mass out here, which is basically the inverse of the curvature of this parabola, is order alpha to the 4th. And therefore, P has to be order alpha squared before the parabola actually hits the continuum. This will be the goal. Okay? And what you see already is that since the energies itself are order alpha squared, however, we have to have a resolution of order 1 here to see it. We need to calculate the energies to the precision of order 1, so to say, to be able to see this curve at all. Okay, so this will be the bottom line. This is the goal, and this is basically anticipating already essentially what we will be able to prove. Okay, but I'm moving ahead a little. So let's go back to the model. Now, what about the effect? So it turns out that there's an effective theory for large alpha, which is actually a classical field theory, or it's partly classical because the electron is still quantum, but the polarization field becomes classical. Right? So if we do that, we arrive at what is known as the Pekar or Landau-Pekar functional. So as I said, the electron is still quantum, so there's still a psi now for the electron. But the field, which was before a quantum field, is now a classical field. So effectively, wherever you saw the A's and the A daggers for the quantum field, you just replace it by a function now, by a commuting object. In fact, well, okay, I call it Z here, but then actually I write everything in terms of the Fourier transform of Z, which I call phi. Okay, so phi is now the classical polarization field. It has a real part and an imaginary part, so it's a complex valued field. And you see that the electron, with this sort of dipole interaction, right, the electron density psi squared couples to the real part of the field, phi, with a 1/x squared interaction. That's this Fourier transform of 1/a. And I think some 2 pi's or something I set equal to 1 here for simplicity. And then the field energy in the classical case is just the L2 norm of phi. That's the analog of the integral of A dagger A, if A is just a classical field. Right? So this is called the Pekar functional, and what I did here, you see, I didn't write down the alpha. There should really be a square root of alpha here, but I ignored it because it can simply be scaled out in the classical model. So the effective theory turns out to have no parameter. I can write down the alpha here in the coupling, but then by a simple change of variables in the length scales, you can just remove the alpha. Okay, so that's why I didn't even write it. What you may have seen also sometimes called Pekar functional is what you get if you already minimize over the possible values of the field. You see, for given electron wave function psi, this is just quadratic in the field, right? So here's something linear, here's something quadratic. So of course, we can easily minimize a quadratic function. So we just complete the square. Excuse me. And what you find, if you minimize over the classical field here, right, you just get this effective self-interaction of the electron with a 1/x Coulomb kind of interaction. Right? That comes from the fact because of the convolution of 1/x squared with itself is 1/x. Right? Again, up to some 2 pi factors. So the effective model for the electron in this classical approximation is simply the one of a moving particle with a Coulomb's density-density self-interaction, so to say, which is effectively generated through the interaction of the polarization field, which in this case has to be integrated, was already integrated out, so to say, on this classical level. Right? And you see, of course, here effectively there would be a coupling alpha in front, but then simply because here you have a gradient, so this is a 1 over length squared, you have a Coulomb like 1 over length, so by changing lengths by a factor alpha you can scale it out, and the energy is proportional to alpha squared, really. That's to be kept in mind, but I dropped it here simply because of this scale. Now, what about this classical model? So this is actually also of independent mathematical interest. You can, for instance, study this function and ask, what about minimizers? In fact, this was an old work by Elliott Lieb in the 70s who proved the existence of minimizers and actually the uniqueness up to the trivial symmetries. Right? So meaning, right, this functional is clearly also translation invariant. If you move psi by a translation, it doesn't change. However, Lee proved that this is, so up to this symmetry, there is actually a unique minimizer. Okay? So this is an artifact, if you want, of the classical approximation, right? Because you have a translation invariant system. On the quantum level, you do not expect that it has a ground state, right? Because after all, it's translation invariant. It's fibers according to the momenta, but the classical approximation actually has a ground state, of course infinitely many by translations. This is sometimes referred to as a self-trapping phenomenon, that somehow the electron, due to the interaction with the polarization field, gets trapped in the potential well that's created by itself. Right? So that's why it's called self-trapping. What is also relevant, actually maybe not really for my presentation, but for the proofs, is actually an important sort of generalization or extension of this work by Lieb, by Enno Lenzmann, who showed that if you look at the Hessian at one of these minimizers, then it's strictly positive up to the trivial zero modes that come from the symmetries. Right? So you look at the minimizer of this functional, and you take the second derivative at the minimum, then you'll get zeros from the symmetries. There will be trivial 3 zero modes from the translation invariance, but away from these zero modes you have strict positivity. So that's what Lenzmann proved, and this, as I said, is actually important for our analysis later. So this is the classical approximation. This is the effective functional, and in what way does it appear? Well, for instance, if you look at the ground state energy of the Fröhlich Hamiltonian, and you look at its asymptotic behavior for large alpha, then it turns out that indeed the classical approximation becomes exact, which you can formulate this way. Since the classical approximation, I already told you, effectively you should really think of alpha squared times the Pk energy, because the alpha scales out. So if you divide by alpha squared, then the ground state energy of the Fröhlich model converges to the Pk energy, which is simply the minimum of the Pk function. This was first proved by Donska and Varadan actually in the 80s, using a very different formulation of the model in terms of the Feynman path integrals. It turns out that this is a nice application. In fact, this was maybe even one of the first applications by Feynman himself of his formalism to statistical mechanics. Maybe it turns out that if you write sort of the model, the heat kernel, so to say, of the model, you can integrate out the phonons. Again, because if there's a linear and a quadratic term, it's effectively just Gaussian integral, so you can do it, and you arrive at an effective self-interaction of the electron. In the path picture, you get, besides the usual Wiener measure just from the Brownian motion, I mean from the Laplacian, you get this additional self-interaction of a retarded, you see the omega is the path of the electron in this path integral picture, and it interacts with itself at some retarded times weighted by this exponential factor. Basically, what Donska and Varadan did is sort of study the asymptotics of this measure for large alpha and large t. I mean, t is sort of the imaginary time. I mean, you look at e to the minus t times h. This will not play any role further in my talk, but this is more of a side remark, that this is another way actually people study the polaron model, and there's also lots of recent developments, which I may quickly mention at the very end if there's time, at the study of these measures. For my talk, I will not actually use them, but they were first used to establish this classical asymptotics, the effective classical behavior of the model for large coupling. Later, Lieb and Thomas actually gave a different operator theoretic proof, which was also quantitative. So they proved that the ground state energy of the Fröhlich model is bounded from below by the classical problem, alpha squared times the Becker energy, up to terms which they could quantify as O of alpha to the 9/5. Okay. There's also a trivial upper bound, by the way. The classical model is always an upper bound, as you can see by a product ansatz. So basically, if you take a completely uncorrelated ansatz, electron times a field, then you see that the field wants to be a coherent state, which is exactly the most classical behavior, the minimal uncertainty states. They give you exactly the classical model. So the classical model is always an exact upper bound. And the challenge is to derive a lower bound, and you see they could do it up to an alpha to the 1/5. This is already sort of shows you the challenge that is ahead of us, right? I told you that we are after this curve. We would like to understand the effective mass and the curvature of this parabola. Knowing the energy to order alpha squared is way worse than what we actually need. We need to control it to something that's small compared to order 1 to be able to see this gap at all, right? Because after the energy plus 1, there's the essential spectrum. So the only way to see this curve is that if you actually know the energy to something little O of 1. Okay. Okay, so let me actually, to motivate what comes, let's actually discuss about possible corrections, right? So this is the classical limit. What could be a next order term for large alpha? It turns out that sort of quantum fluctuations about the classical limit. Right, so you can imagine that the classical picture is sort of really that you minimize the field, you ignore the uncertainty principle, so to say you minimize the field, but then of course you know there's really quantum mechanics, there's an uncertainty principle, there will be fluctuations around the minimum, and to leading order they will be quadratic, so you're going to get a system of lots of harmonic oscillators. So to quantify this, it turns out that we have to go back to the Becker functional of the field, because it's actually the fluctuations of the field that will be important. Effectively, what happens is that at large coupling, there's sort of a separation of scales. So the electron will be the fast degree of freedom. The electron will always be sort of in the instantaneous ground state of the potential well that the field creates. But the field will be the slowly varying variable. So if we look at quantum fluctuations, it's actually the fluctuations of the field that will be essential, not the one of the electron. They will be higher order. So we should not minimize over the field, but we may freely minimize over the electron. So if we go back to the Becker functional, maybe just remind you 1 second, right here it is, the electron and the field. We can, of course, instead of minimizing over the field, we can also minimize over the electron for a given field, right? The behavior of the electron is quadratic, so minimizing over the electron for a given field is just saying compute the ground state energy of this effective Schrödinger operator, right, Laplacian, and you have a potential which is simply the real part of the field convolved with 1 over x squared. Right? So therefore, once I minimize over psi, what I get is this effective Becker functional for the field, which as I said is the ground state energy of this effective Schrödinger operator, and then of course there's still the field energy integral phi squared. Okay? And now if we minimize this over all phi, of course we get the Becker energy, but let's not just minimize, let's actually expand around the minimum, right? So we look at the minimizer, let's call it phi Beck, we expand around it, so there will be some quadratic fluctuations around it, right? And this is simply the Hessian of this functional at the minimizer, right? And this Hessian will be some operator on L2, right? Which is between 0 and 1. It's clearly positive, because after all we're expanding on the minimum, so the Hessian has to be positive. It's less than 1 because you see, if you look at the functional, this guy will give you a 1, but this guy will be concave in phi, right? Because it's the ground state energy of a Schrödinger operator depending linearly on phi. So this will be concave on phi, so the second derivative will be negative. So therefore, this h will be sort of 1 minus something. So therefore, it's between 0 and 1. Okay? And actually, as a consequence of Lenzmann's work, is that this guy has exactly 3 zero modes and then a gap in the spectrum above 0. So if we take this into account now, and we can imagine these guys, therefore will be effectively, we will have quantum oscillations in this potential, so we'll have a bunch of harmonic oscillators which move, so to say, in a quadratic potential with sort of frequencies given by the spectrum of this Hessian. Then we're led to the following prediction or conjecture, namely that if we expand the ground state energy of the Fröhlich model for large alpha, then beyond the classical approximation, we should sum up the 0-point energies of all these harmonic oscillators. And they turn out to be order 1, actually, right? So you see here there's an alpha squared. The next term should be order 1, so whatever comes left should go to 0 here as alpha goes to infinity. And it turns out, just if you do it precisely, what you really should get is the difference of the 0-point energies of this guy and the 1. And it actually turns out that this object is the one that is trace class. So you see I write here the trace, so this is the sum of the whole spectrum of the square root of the Hessian, right? Because harmonic oscillator, right? P squared plus omega squared q squared, you should think, right? That's energy, the 0-point energy is omega. The potential is omega squared, so you have to take a square root, so it's the square root of this guy, and the difference to 1, actually, that's the one that is trace class. So it turns out that this Pekar Hessian actually is a trace class perturbation of the identity, so this square root of h minus 1 is actually trace class, and summing up these 0-point energies leads to this number. Okay? So this would be the expectation that actually there's an order 1 correction coming from these quantum fluctuations, which should change the ground state energy by this amount, and whatever else is left should be a little over 1. And this formula you can actually find in the physics literature, at least going back as far as the 60s. The second thing I wanted to talk about is the effective mass, right? I already introduced it. I told you it's basically the inverse curvature of this parabola. And going back to the classical picture, you can actually arrive at a prediction which goes back to a paper by Landau and Pekar, that the effective mass should grow like alpha to the 4th. I already mentioned there's also a concrete prediction for the prefactor, which is simply the gradient norm of one of these Pekar minimizers. This is the Pekar field. Okay. In any case, this is just some explicit number, and it should go like alpha to the 4th. It's not actually immediately obvious how do you derive this from the classical Pekar function, but a simple hand waving sort of will give you this formula. So this is clearly a prediction. So as I said, the definition is as follows: that you basically look at the ground state energy curve as a function of momentum. You expand it around momentum 0, right? So you expect it to be quadratic, and the coefficient in front of the quadratic term you call 1 over 2m. Okay? By definition, that's what m is. Okay? So what we expect, therefore, if we take these two results together, right? The correction, the quantum correction to the ground state energy coming from the quantum fluctuations, plus now the expectation that there should really be a parabolic behavior with an effective mass of this size, then what we would really like to try to prove is a formula like this, right? So the classical Pekar energy, the quantum corrections, and then a parabolic behavior with the prefactor alpha to the 4th. And for what window, right now coming back to the picture, what I already anticipated, this can be expected to hold in a window of momenta of order alpha squared, right? Because we know that the essential spectrum starts exactly at 1 above the ground state energy. So clearly this curve has to dive into the continuum once this p squared over alpha to the 4th is 1, which exactly is the regime that the momenta are order alpha squared. Okay. All right, so this is the motivation, and the theorem that we have basically confirm exactly that. Okay, so the theorem says that the identity I just wrote down is true. I wrote it as two theorems because they're really two separate papers with two different sets of authors, and actually also very different methods. But and one gives the identity as an upper bound, and one gives the identity as a lower bound. Right. So let me go through them separately. So the first is joint work with David Mijurskas, who is a postdoc at IST, and Krzysztof Myszliwi was a PhD student. So there we looked at the upper bound, and we sort of constructed appropriate trial states to prove this formula as an upper bound. So here it is again. If we look at the ground state energy of the Fröhlich model at fixed momentum p, then we get as an upper bound the classical expression alpha squared times Pekar energy. There's the order 1 quantum correction from the quantum fluctuations, and then we get actually exactly this curve that I drew here. It's the minimum of two things, namely 1, simply that's the gap to the essential spectrum, and the parabola, which is p squared over 2 alpha to the 4th times this prediction, the Landau-Pekar mass. Okay? And the upper bound is sort of uniform in the momentum, but with an error term that vanishes as alpha goes to infinity. And in fact, the bound we got was basically alpha to the minus a half up to arbitrary small epsilon. I will not have time to say much about the proof, but let me just say that the complication comes from the fact that we really have to fix the total momentum, right? So we have to work, so to say, in this fiber picture, where actually we fix the total momentum, and the complication comes from the fact, in some sense, that the classical picture, as I explained, or I just mentioned, at least to the side, emerges simply from an ansatz where you take a product ansatz, electron times field, and the field is in a coherent state. Now, this is not a state of a fixed momentum. Right? This is actually superposition of a whole set of momenta, some sort of wave packet. So now you actually have to sort of fiber this into the sectors of different momenta, even just to get, so to say, the main term. But then you have to modify it to actually get the quantum fluctuations right. And so it's, at the end, it's actually a huge computation. I think it took more than 50 pages to do it. So it's not at all straightforward. Well, maybe the ansatz is sort of intuitive, but actually carrying it out was quite a major effort. The corresponding lower bound was proved together with Maurice Brooks, who was also a PhD student at IST. It reads the same, right? Except that now the inequalities are turned around, so it's a lower bound. Everything looks the same, except the error term we got is a little bit worse. In fact, it's probably so much worse that we didn't actually even bother to work out what precisely the exponent is. There is, so we formulated at the end as saying that there is a W such that you get uniformly in the momentum, you get alpha to the minus W. W is probably some very small number. Okay. So these bounds together sort of basically confirm this picture, right? I mean, up to a small window, of course, because we always have these additive errors vanishing in the limit alpha to infinity. We basically establish exactly this curve with the predicted curvature and up to small error terms. In particular, it proves, so to say, this what I formulated as a conjecture before, this prediction maybe of defined in the literature by Alcock, that we can compute the ground state energy of the Fröhlich model up to terms little o of 1, right? As I said before, compared to Lieb-Thomas, I mean, they got to alpha to the 9/5. We actually get to little o of 1, right? So in particular, you can formulate it this way, that if you look at the difference between the ground state energy of the quantum model, the Fröhlich model, and its classical approximation, there's this order 1 correction coming from the quantum fluctuations. This is an immediate consequence, of course, of these two theorems, evaluated at p equals 0. Yes?
Is there missing a minimum?
Yeah. There is a minimum missing, yes, thank you. Yeah.
So in both results, the error is uniform in p?
It's uniform in p. Of course, in some sense, this is not the hard part, because we know, so there are several things we know a priori. I should have maybe mentioned that. So it is known that E of p is minimum at p equals 0. This is always known. And it's also known that the essential spectrum starts at 1 plus the ground state energy. Right? So in some sense, large momenta is trivial. It's clear that nothing happens out here. So the uniformity is sort of not the hard part. But yes, the statements are completely uniform in the momentum. And I wanted to just briefly refer to earlier work. So this proves this conjecture, and we had proved something similar in simpler models, namely sort of confined models, where we sort of defined away the infrared problem, if you want. Joint work with Rupert Frank and also with former student Dario Feliciangeli. We had looked at confined models earlier where we could prove an analog of this formula, but now we can actually do it for the full world. Let me maybe say also just a couple of words about the lower bound here. So, as I said, it's actually very different in terms of methods from the upper bound. And in fact, in some sense, we avoid using the fiber decomposition at all, right? Which is, of course, can't quite be true, because at the end we get the lower bound on the energy as a function of momentum. The problem is somehow that if you, despite the fact that the fiber Hamiltonians look deceptively simple, it's not obvious at all how to use them to relate them to the classical effective model. Right? So basically, as I said, the classical model simply arises by an ansatz, a product ansatz with a coherent state in the field, which is not compatible simply with the fiber decomposition. So I think it's fair to say that nobody knows how to even derive the classical approximation, the leading order term for the ground state energy of Fröhlich in the fiber decomposed picture, so to say. I think the only way we would know how to do it is to go back to the full model, reintroduce the electron coordinate, and do it in the nose way. So effectively, we're still doing that. We don't actually know how to work precisely in the fiber picture. But we use the fact that for a lower bound, of course, we can relax things a little bit. I mean, we may as well sort of localize, if you want, an energy momentum space. We can look at states that have some finite width also in momentum. So you can imagine we're trying to effectively look at states that are sort of localized in some non-vanishing region in the energy momentum plane. And effectively, it's not actually fix the momentum, but let it fluctuate a little. Right? In fact, one thing you could try to do, which will not work a priori, but effectively we make it work in sort of a truncated model, you could try to put the constraint into the system by a Lagrange multiplier, right? That's a standard thing. You minimize with a constraint. Now you want to minimize with the constraint that you have a given momentum. You're in this sector, right? So you could say, well, let's add the momentum as a Lagrange multiplier and minimize unconstrained, right? Now, why does that not work? Well, because effectively what you're doing, if you're thinking about it, so of course you put in the Lagrange multiplier, at the end you optimize over the choice of the Lagrange multiplier. What you're really doing is you're taking a double Legendre transform of the curve you want to compute. So this works perfectly fine if your curve is convex, right? Legendre transforms are good for convex functions because doing them twice, they just reproduce the function. But here, if we're trying to compute the Legendre transform of this function, what we get is a trivial constant function. Right? The Legendre transform of a double Legendre transform of any function gives you basically the convex envelope of the function. Right? So the largest convex functions lying below the function, and you can easily convince yourself, in this case, that's just the constant function, right? You cannot possibly increase because you would not stay below the constant. So actually doing it this way will not work. It will give you just the constant, it will just give you the ground state energy at p equals 0 at the lower bound. But effectively, we're using this method, but sort of in a truncated way. We're effectively truncating the allowed values of the phonons. You see that the picture of this curve flattening out here always comes from the fact that I can for free add one phonon at an arbitrary momentum at an energy cost 1. Right? I put one phonon behind the moon, doesn't interact with anything, it costs me energy 1, and I'm already in the continuous spectrum. But you see, what you need for that is phonons of momentum of order alpha squared, or larger out here. And it turns out those are actually not really relevant for the problem at all in here. There actually the relevant phonon momentum is sort of order alpha. There will be lots of phonons, that's why the total field momentum is huge. But the individual phonons will actually only have momenta around order alpha. So we can put in some cutoff between, if you want, alpha and alpha squared, disallow these phonons altogether and get rid of this problem altogether. And then it turns out the method of Lagrange multiplier can be applied to this cutoff model, and this is effectively what we're doing. So this way we're avoiding working in the fiber picture. Okay, this was just a number of side remarks for those of you familiar with these methods. Okay, so as I mentioned, so first consequence was we can compute the ground state energy to precision little O of 1. What about the effective mass? Well, the theorem, of course, really gives you this parabola, right, up to small errors. So in particular, it implies that if you look at this quotient, right, you look at the energy of momentum p minus at 0 divided by p squared, and you see I already put in p's of order alpha squared. So I put in the alpha squared factor here, right? So we know that this thing is actually order 1 now, right, or order p squared, right, because it's p squared over, it's the square of this thing over alpha to the 4th, so that leaves the p squared. So this ratio, if we now send alpha to infinity at fixed non-zero p, this will converge to this prediction, the Landau-Pekar mass. I wrote here p equals 0, but this is artificial because actually for any p less than whatever, this fixed number, this ratio will converge to the Pekar mass, right? Because in the limit, this is an exact parabola. Right? This is an immediate consequence of the two bounds we had. Now, if we look at the usual definition of the effective mass, however, usually people just say, well, take the curvature at 0, right? Just take two derivatives at p equals 0. Of course, we cannot do that, right? Because we only have bounds on this curve, which give us sort of a little window, which of course doesn't allow us to take derivatives. So strictly speaking, we cannot really make a prediction about the effective mass defined as the curvature at 0, because in some sense, all we know is the global curvature over this natural window of order alpha squared. Right? So to define the effective mass, usually one would like to reverse these two limits. Right? This would be the standard definition. You would just define the effective mass even for fixed alpha, right, as the curvature around 0. So you would first take the limit p to 0 of this ratio, and then you would study the asymptotics of this for large alpha. So much less is known about this, but actually also we can make some deductions. So let me just briefly mention sort of the work of this in recent years. In fact, as I said, the prediction a long time ago, going back to the 40s, I think Landau and Pecard, is that this should grow like alpha to the 4th. I think only a few years ago, together with Elliott Lieb, we managed to prove that it grows at all. Meaning that this quantity actually does diverge as alpha goes to infinity. Since then, a number of quantitative lower bounds have appeared. I don't mention them all here. Let me just mention the most recent, which was posted a few months ago at the archive by Seiringer, who can actually prove almost the correct divergence. So he got a lower bound of order alpha to the 4th up to some logarithmic corrections. I think there was a log alpha to the 6th. Whoops, sorry, I'll come back to that in a second. But there were some previous works also by Betz and Polzer. This is sort of the latest. And this actually uses, and this comes now briefly back to what I mentioned before, this path integral picture, which was recently in the last maybe 5 years or so, there were a number of papers by Mukherjee and Varadhan who looked again at this path measure coming from the Feynman-Katz formula, or the Feynman path description, and studying is asymptotics for large alpha, probabilistic description. This is the main input that Seiringer uses actually to get this lower bound with the almost correct asymptotics. In terms of upper bound, interestingly, it turns out that our result does imply the right thing as an upper bound, and this is due to an also very recent, very nice, and maybe even somewhat surprising work by Polzer, who showed that the curve p squared maps to E of p. So this curve, but not as a function of p, but p squared, right? And that's what it is, because after all, everything is rotation invariant, and so you can look at the map. You can think of this as a function of p squared. It turns out that he could prove that this is concave for any alpha. So, right, as a function of p squared, of course, this would look here, a priori, this would look linear, right? Because this is quadratic. So as a function of p squared, you would have something linear. So clearly, the limit is concave, but actually he proves for any alpha it's concave. And you know, once of course you know it's concave, you know that the curve cannot start too slow, right? Because it can, if it's concave, if it has a too small slope, it can never pick it up again. So knowing our global bound, together with the fact that as a function of p squared is concave, immediately gives you a bound in one direction. It immediately tells you the upper bound, that this effective mass asymptotically cannot be larger than the predicted value in the alpha to the 4th times this Pecard. The corresponding lower bound, as I said, is still missing. Equality is expected here, clearly, but the upper bound actually follows from our work, together with this nice concavity result. Okay. Then maybe one more last result, which is also sort of a consequence, not of the results now, but it's a consequence of the method. It turns out that, as I said, yes, this upper bound construction that we did with David and Christoph, one can also generalize it to not just look at the ground state energy, but actually look for possible excited states of the system. Right? And it turns out, and this actually came as a surprise to us when we observed this, because I think there's no trace of any prediction of this in the physics literature, interestingly. It turns out that there are lots of excited states if alpha is large. So this is actually sketched in this picture. Basically what happens for large alpha, that is, you don't just have this one curve that goes below the essential spectrum, the ground state branch, but actually additional branches will appear here. maybe you can imagine that for large alpha they sort of come out of the continuum, there will be additional branches. Okay? And in fact, what we can prove, and that follows from our upper bound construction, there will be lots of them. So if you count, for instance, take p equals 0, if you count the number of eigenvalues below the essential spectrum as a function of alpha, then we can prove that this diverges actually as alpha goes to infinity. So the number of additional excited bound states, sort of stable excited polarons, becomes arbitrarily large for large coupling. Okay, so here it's formulated as a theorem, so this was jointly done by David, put in the archive a few months ago. So here's the sketch of what happens, but if you want to formulate it precisely, it's saying, so look at the discrete, the discrete spectrum of the Fröhlich Hamiltonian at fixed total momentum P. Look at its size, so simply the number of eigenvalues below the essential spectrum here, and either for p equals 0 you can say, or more generally you can say for any p that grows slower than alpha squared, so in some sense in this picture we stay close to the p equals 0 axis on that scale of order alpha squared, then the number diverges as alpha goes to infinity. So this is sketched in this picture. In fact, the upper bounds that we get are also exact parabolas with the same curvature as the ground state curve. We only know this as upper bounds, really, and in fact, where they come from is sort of, should not be surprising from what I said, because if we look, as I told you, that the picture of the polaron at large coupling is that you're close to the classical minimum, the minimal value of the field, and then you have the quantum fluctuations that are described by sort of the, effectively you get a Bogoliubov kind of Hamiltonian. You have a quadratic Hamiltonian, a bunch of harmonic oscillators, and of course these oscillators you can excite. Right? And if I go back to the description right here, the excitations, so here was the heuristics, right? The excitations are described by this quadratic function, this sort of, that's the potential well, and we see here the frequencies are given by this Hessian of the Becker functional, and all they have lots of frequencies strictly less than 1. Right? In fact, I mean, this guy is a trace class perturbation of 1, but it's infinite rank. So there are infinitely many eigenvalues below 1. Right? And all these effectively lead to harmonic oscillators that I can excite. Right? So there are lots of excitations I can make in this system, all with energy strictly less than 1, namely the eigenvalues of this Hessian. Right? So that's the prediction, at least for very large coupling, and therefore we can use those to construct trial states that give us exactly these expected energies as upper bounds. And of course, upper bounds are all I need to compute to evaluate the discrete spectrum once I have a global lower bound, which the theorem together with Morris will tell us. Right? Once I know a lower bound on this, I have an upper bound on many eigenvalues, then I know that they are actually discrete eigenvalues in the window between the ground state energy and the essential spectrum. Now, interestingly, I think one reason this has not been observed, even in the physics literature, is that potentially alpha might have to be very large to see it. We don't actually know. One would have to do probably some numerics to find out how large alpha actually has to be. In fact, in the physics literature, there are some papers where people did some sophisticated numerical study, but typically it turns out that alpha around 10 or something is about the maximum they can reach, because things otherwise numerically just become way too expensive. And in this window, actually, they have not seen excited states. And this is also something I then try to understand, namely what happens for small alpha. This is just a side remark now, but for small alpha, techniques are very different. In some sense, one is in a perturbative regime, so I first thought naively, actually, this must be easy to figure out what happens for small alpha. It turns out it's not easy, but one can figure out what happens. And in fact, there are no excited states. Okay, so for small alpha, this is what I recently proved. So I formulated it this way: the discrete spectrum is just the ground state energy. In fact, I could really, strictly speaking, only prove this at p equals 0. But of course, you expect that if there are no excited states here at p equals 0, there should also be none out here. I mean, you don't expect something crazy like here, but strictly speaking, this is not known. But for p equals 0, I managed to prove that for small alpha, there are no excited states. So alpha really has to be larger than some critical value before you can actually see them. And what this critical value is, And in particular, whether this is sort of relevant in physics, where you have to keep in mind alpha is in some sense some kind of material parameter. Alpha is not really something that they can vary effectively in the lab. Depends on the material they study. So whether there are actually materials where alpha is large enough to see this, we still don't know, because we don't know how large alpha has to be. Okay, so maybe I'm basically done. So I think I have just a conclusion slide here. So let me just summarize about the results, right? So what we look at is the Fröhlich model of a polaron, which in particular spectral analysis of this model, which means we study the joint energy momentum spectrum, which we can do because of the translation invariant of the model. And the goal was basically to derive upper and lower bounds on the ground state energy, or more precisely the ground state energy as a function of the momentum. In particular, in order to do this, we needed to sort of zoom in, if you want. We needed to know the energy here in this direction up to terms little o of 1 in order to resolve, so to say, this effectively small gap where things become interesting. So we managed to compute the ground state energy, so to say, two-term asymptotics up to terms order little o of 1. And in particular, the bounds confirm the expectation that the energy is basically the energy of an effective, much heavier particle, namely one with an effective mass that's increased according to the Landau-Pekar prediction alpha to the 4th times this explicit constant. And as I just said, a generalization of this, or looking closely at the upper bounds, actually shows that we don't just have one curve, we actually have many curves. There will be lots of eigenstates appearing below the essential spectrum at large coupling. And finally, one remark is that there is a corresponding time-dependent problem also. One can look at the time evolution generated by the Fröhlich Hamiltonian, right? And one can ask whether for suitable initial states one can derive as an effective model the corresponding time-dependent Landau-Pekar equations, right? Which is simply, basically, if you take the classical functional wrote down, you can think of this as a classical dynamical system. So there is an effective Hamilton's equations for this system. They are known as the Landau-Pekar equations. And what we actually did a few years ago together with Nikolai, David, Simone Rademacher, and Benjamin is to derive these Landau-Pekar equations as effective descriptions of the dynamics. But this is actually something I believe I talked about here 2 years ago, so I will not repeat it here. Okay. Thank you.
Could you please go back to the theorem on excited states? Right, so this reminds me a little bit of the work that Georgi Raikova and collaborators did some years ago, in which you have the Landau Hamiltonian in 2 dimensions, which consists of infinitely degenerate eigenvalues at the Landau levels. So what they do is that they add perturbations that somehow start splitting these eigenvalues, and what they then do is that they study the accumulation function. So they somehow take an interval, and then they start by getting to the accumulation point, and they describe the asymptotics of this function. So do you think that you can do something similar?
It's a bit different, because I think at any finite alpha we expect that there is only finitely many eigenvalues. So there's no accumulation here really. Only if I take a formal limit alpha to infinity, then I will get infinitely many curves. And I think we know precisely how they accumulate, because it's basically the spectrum of this Hessian, of the classical functional, that determines all these values. But this is, strictly speaking, really only limit to at alpha equals infinity. At any finite alpha, we don't know this, but we expect that at any finite alpha there will only be finitely many eigenvalues.
So do you know if you can more or less describe the gaps between the...
We know exactly what to expect. So we know exactly what this curve should look like, because they're exactly the spectrum of this Hessian. We only, strictly speaking, only know them as upper bounds. So the lower bound is still missing, but the prediction is very clear what they should be. But this is only up to terms always of alpha to some power, some negative power. So there's a little wiggle room, and we don't know how far it wiggles until, eventually, once it wiggles out of the interval, then they're not there anymore. So I think that's the picture to have in mind.
Another question? have one. Do you have any guess for the number of the eigenvalues as a function of alpha?
No.
No, not at all.
No, I mean, of course, strictly speaking, we have a bound. Our theorem is quantitative, so we will get a bound, but it's probably very bad, and so we don't really know. As I said, there will be in particular a critical alpha before even the first one appears, and there we also don't have a good prediction. We hope that somebody can do the numerics and actually find out, but it's apparently not easy, you see. So at large alpha, simply you have a lot of phonons. So the number of phonons increases like alpha squared. So effectively you have a many-body problem, and once alpha is 10, that means you have to deal with 100 phonons, and that's numerically already extremely expensive. So I think that's about as much as they can do with their fancy Monte Carlo algorithms, but they can't go much beyond that.
Yeah, just again about these curves. So, but then because of, so I mean, the curves becomes more visible in a range of p, I guess, which depends on alpha, or because of the error you have in your energy asymptotics.
That's right. So you have to. So I think maybe the picture. No, I think it should even. So I think the picture is the upper bounds give simply the same parabola that we get here, shifted upwards. Right. So therefore, depending on how far you shift, you see how far they will go. But of course, they come with a little wiggle room, and that tells you.
This wiggle is because of the error you have in the upper
Exactly.
bound. Okay. So this means if you choose p as a function of alpha, which is like alpha squared or a bit less than that, then the error is much less.
Exactly, and that's why we have this formulation. As long as p is much smaller than alpha, we're always effectively close to here, and we'll get arbitrary many eigenvalues as alpha goes to p.
Okay, thanks. Yeah.
That's very natural, simply from the fact that all these curves have the same curvature.
So the mass is the same.
So effectively, at least the upper bound, we get the same effective mass, and that we expect that, yeah. Because you see, the reason we expect it is that effectively this decouples. You see, the excitation is an internal excitation. You can imagine something a bit like analog of a freely moving atom, right? It moves and has internal excitations, but the excitations don't affect the mass of the object. So here it's similar. In some sense, the mass is a degree of freedom that comes from the translation invariance, and effectively, at least in the limiting model, effectively completely decouples from the internal motion, and therefore the effective mass will be expected to be the same even for the excited states.
And can I ask another question? So in the Selke result, I mean, can he also access energy asymptotics, or somehow he has a formulation for the mass? And then
there's a formula. So effectively, they write down this path integral formulation. You take actual two derivatives, so really looks at that, and then there's a formula for this, and then he asymptotically can evaluate this formula. So I don't think they have access at all to the energy with this method, as far as I can tell.
And that formula is not useful for your, I mean, it's totally different
It's
methods.
completely disjoint. I mean, it's also what I find particularly curious is this proof, this was Polzer, that d squared maps to EFP is concave. There must be an operator proof of this.
So that is also based on,
He
okay.
uses the same formulation. He uses exactly the identity that you get out of this path integral description. And it's extremely elegant, but I don't know, I don't really understand it because I don't have a good feel for it, and I would really love to have an operator proof of this, but I tried and I failed.
On the energy estimates on page 9, I believe that the error term dominates over the kinetic energy term when p is not close to alpha square.
So, I mean, if
p
p is very close to 0, then you would not see this one anymore compared to that. That's what you're saying, right?
Yeah.
But this is, I think, that's my wiggle room, right? So in this picture, I'm saying, effectively, I know this curve only up to a little error. So of course, if you stay very close, then I can't really resolve this. That's why I cannot take a derivative. I cannot resolve this curvature. So you're right. If p is very close to 0, then I will not be able to distinguish p from 0 and very, very small power of alpha, because it will be washed out by the error.
In the upper bound, do you have a sense of what are the higher order phenomena that are in the error term?
No. Although, so it's a bit tricky. Although it's not hopeless. So actually, there's, I think, very recent work or work in progress by David and Morris, who look at a simpler model in this kind of confined polaron where you have only discrete spectrum, and they actually claim that they can get an asymptotic series for the ground state energy at p equals 0 with arbitrary inverse powers of alpha, some kind of asymptotic series. So if you had that here, maybe there's a hope that you could actually really resolve things to such a way that you could take a curvature at the end. But I don't know, it's tricky. So it's not obvious. But, I mean, the point is simply we derive upper and lower bounds for the energy as a function of p, right? But we don't really know how smoothly things depend on p effectively.
At least for this term, is there an interpretation in perturbation theory as for the mean field expansion? When you write the expansion for the mean field ground state energy, you can interpret the terms in perturbation theory, the terms of the energy in 1 over n. Like if in the results on the mean field energy, ground state energy in powers of 1 over n,
Yeah.
interpret the various terms in as perturbation.
Yes, so exactly, that's exactly their picture. So if you have the confined system, then you have discrete spectrum, and then you have energy gaps, and then you can just think of basically taking whatever correction terms that we estimate here into account using perturbation theory. That's exactly...
Can you interpret this one, the mean in perturbation theory? As
No, because this one, you see, this picture is a bit different. So this, as I mentioned before, the p squared here, this is in fact simply, in some sense, the 1 degree of freedom, I don't know, like the Goldstone boson, the thing that decouples, that comes from the translation invariance. That gives you a parabola, but of course you know that the picture has to break down once you dive into the essential spectrum. That gives you this formula, right? But what you're asking now, I think, is something different. I mean, so you could even take p equals 0. This term is not there, but you ask sort of say the higher order terms, and you might hope that they come from a perturbative expansion of whatever terms are left as a perturbation of what we know, right? But the problem is here that we don't have any energy gaps because of the translation invariance. So we wouldn't know how to make, it would be difficult to make this precise, but I think maybe if you write down a formal perturbation theory, they probably give you some asymptotic expansion, which there's a good chance that that's right, but we wouldn't know how to prove it.
Okay, so let's thank Robert.